calm serenity of life is the exception, not the norm, and to the reality of the universe. So, okay.
Thanks, Richard.
I'm going to work on the lights here.
Can everybody see the slides already? More or less. I'm Jeremy. I graduated from Christian Brothers in '98 in the engineering program. I actually took classes, in this actual classroom. I believe I took digital design in here. So after graduating, I went to Starkville, worked for 11 years, 9 of them at a semiconductor company, so I come from a technical background. Astronomy has been my #1 passion since I was very young, and it's a hobby. So there's a lot that I can learn and benefit by being a part of this group too. I know a lot of you guys have telescopes, you build your own telescopes, and been in the game a long time. I'm more of a naked eye astronomer. I like to know where things are in the sky, and I do a lot of research, I do a lot of reading, and really it's just something that fascinates me. So when you're looking at the sky, it helps to know not only where things are, but where certain objects are in the distant past and the impact that they've had on the universe. And I think that's the thing that fascinates me the most about astronomy, is when you can look at a constellation and not only see the individual stars that make up the constellation, but know specifically what those objects are like, how big the stars are, how massive they are, what would happen if they were to blow up. Stars that supposedly have planetary systems, maybe stars that are binary systems. The universe is very strange, very bizarre, very, very violent. And I know there's a lot of theories out there about life in other parts of the galaxy, other parts of the universe. The more I study astronomy, the more I'm convinced that it's a miracle that life exists anywhere in the universe, given how violent a place it is. And it's just, and that's really what tonight's topic is about. It's a fun topic to work on because we're really just going to kind of relax and go through some of the events in our past, and really both recent and far back in time, that have had a significant impact on the universe and our understanding of the universe. And I love this quote by Chicxulub Impact. The calm serenity of life on Earth in many ways is the exception and not the norm to the way the universe really is. We're just kind of uniquely positioned in our galaxy off the Orion Arm, a little hole where we're just far enough away from some of these massive stellar events and massive explosions that life is able to exist and flourish and survive here. And of course, someday that will all change when our sun dies. And we're just built into the universe is an inherent obsolescence, regardless of how long human beings and life exists, regardless of how long our Earth exists. I mean, we just have to eventually grasp the reality of our own mortality. Chicxulub Impact, by the way, is one of the leading hunters of supernova in the universe. I mean, this guy literally gets paid to look for supernovas. And he's part of a research team at the University of Berkeley in California. A supernova is a massive star that explodes. One goes off about once every second somewhere in the universe. But on average, it occurs somewhere between once every 50 and 100 years in our galaxy. We'll talk more about supernovas later. But what we're going to do tonight is we're going to do a countdown of 10 of the biggest blasts in the history of the cosmos. And it's going to be both discrete events that have occurred, and then more importantly, think about the category of the actual event, because these kinds of things are happening all the time. So, and when we're talking about blast, what we're really talking about is a tremendous release of energy all at one time. So that's really what we're talking about when we're talking about a blast. It's just a tremendous liberation of energy all at once. And there's really two main forms of energy that we're going to talk about. Kinetic energy, which is the energy of motion. Anytime you have planetary collisions, whether it's asteroids or meteors, things slamming into each other, the energy that's released is equivalent to 1/2 mv squared, where m is the mass and then v is the velocity. So the more massive an object is, the more energy it has. And then, of course, the faster it's moving, the more energy it has. And then when we're talking about stellar and galactic events, we're talking about electromagnetic energy. And Einstein's famous equation, E = mc². Basically what it states is that energy and mass are directly proportional to each other. And the equivalent energy that's contained in an amount of mass is equivalent to that amount of mass multiplied by the speed of light squared. So the bottom line is, if you have a small amount of mass at rest, it's actually equivalent to a tremendous amount of energy if somehow that mass could be converted into energy. And that's, of course, the processes that drives nuclear weapons, stellar and galactic events. Stars are essentially factories which are converting matter into energy all the time. And then conservation of energy, meaning the law of conservation of energy is that that energy cannot be created or destroyed. It can be converted from one form, gravitational energy, into another form, like electromagnetic energy. But the net result is not a loss necessarily, it's a conversion of energy from one form into another. So just a little background. When we're talking about planetary events, kinetic energy. When we're talking about stellar events, electromagnetic energy. So, as a little background, AN-602 is the most powerful nuclear bomb ever detonated on Earth. It's actually a Soviet nuclear weapon. And the equivalent energy released was 50 megatons, 1,400 times more powerful than the combined energy released during the Hiroshima and Nagasaki bombs that destroyed those two cities. The amount of energy that we're talking about tonight in some of the events is going to dwarf this. This is not even a speck in comparison to some of the biggest blasts in the history of the cosmos. And how about our sun? In 1 second, our sun churns out more energy than has been used in all of human civilization since the dawn of time. So just a frame of reference. Most powerful nuclear weapon, the energy liberated by the sun in 1 second. So getting to our countdown, number 10 on the list is called Jupiter Impact. Most of you remember this event. I remember it back in 1994. A comet called Shoemaker-Levy 9 got close to Jupiter. Jupiter's gravity snagged it in and broke the comet up into separate fragments, which eventually slammed into the planet. And you could actually see the scars on the surface of Jupiter through binoculars and even through a telescope. Maybe some of you have even saw this event. So, and it was all over the news. Summer of '94. It was in magazines, and when the comet hit, the largest fragment was about a mile wide. And when it struck the planet Jupiter, it released energy equivalent to 6 million megatons of TNT. So to put that in perspective, imagine taking every bomb on Earth, all the nuclear weapons, every bomb that we have, and blowing them all up at one time. This fragment was 100 times more powerful or more energetic than blowing up every bomb in every corner of the Earth at once. So that gives you an idea of why it's nice to have Jupiter in our solar system and why you need a good Jupiter in order for life to exist. Jupiter's our big brother, and it acts like a filter between the outer solar system and the inner solar system, so that when some of these comets and meteors and asteroids get off track, a lot of times the gravity of Jupiter will snag it and slam it into the surface of Jupiter rather than us. Of course, it can work the other way too, because Jupiter is an equal opportunity abuser. So sometimes it snags these things and spares us, but other times it'll snag when they just fling them out. And they can end up getting on a collision course with the Earth. But asteroids and comets are things that we need to just be aware of. In fact, there's an entire section of astronomy that's devoted 100% to this. It's called NEO, Near Earth Objects, where you have scientists who are scanning the skies daily and cataloging these things. And the idea is, if you know where they are and you know where they're moving, and you can spot them early enough, then you can proact instead of react. So asteroids that get on a collision course with the Earth, a lot of times we have a lot of warning. Several years, sometimes even several decades before the reality of possibly getting impacted by these things happens. And you don't want to blow them up. I mean, we've seen the Hollywood movies, Armageddon, and what was the other one? Deep Impact. Absolutely contradicts reality. You don't want to blow these things up. The idea is to nudge them just a little bit. And there's several techniques that you can use. So, but still, it's not easy. Things have a lot of mass, they're on a collision course, and plans are in place right now to respond if and when the next asteroid gets on a collision course. Asteroids are not that big a deal. Now, in 2029, just to give you some idea of when the next one's coming, there's an asteroid that's going to be passing very, very close to Earth. It's called Apophis. It's not as massive as this one is, but it's massive enough that if it did hit us, it would do a significant amount of damage. To give you an idea of how close Apophis is going to come, in 2029, it will be closer to the Earth than the satellites broadcasting the Olympics, for those of you who are watching the Olympics tonight. It won't hit us, but if it passes through a section of space called the keyhole, which is a gravitational window, it could set us up for a collision 7 years later in the year 2036. So the odds of that happening are pretty slim, 1 in several 100,000. But it gives you an idea of how close some of these objects can actually come to Earth. Well within the distance between the Earth and the Moon, which, quite frankly, is a little bit too close for comfort. So, but asteroids, we have a pretty good handle on, and we have plenty of time to respond. Comets are a different story, because a lot of times they have a very elongated path, and we don't see them until quite a bit further along in the process. So typically you're talking a couple of years, best case, and maybe even be a few months, and by that time it's too late. So comets and asteroids, things to be concerned of, and they release a tremendous amount of energy, as was the case in 1994 with the Jupiter impact. Now, moving along, number 9 on our countdown, death from the sky. And this is actually the theory for the impactor that wiped out the dinosaurs. So supposedly 65 million years ago, there was an impactor. This is actually me at the Meteor Crater earlier this year. So this is in Arizona, and this thing is about 3/4 of a mile wide. It was formed by a nickel iron object about the size of half of a football field that impacted the Earth about 50,000 years ago. And it was traveling at about 12 kilometers per second and left this hole in the ground. So it's pretty impressive. Cost me $16 to get this picture, but you're only young once, so you get it. But this crater is nothing compared to the one on number 9 on our list, which is the Chicxulub Impact. So 65 million years ago, supposedly, there was a 6-mile wide space rock that slammed into the area off the Yucatan Peninsula in Mexico. And this crater was discovered in 1980 by some geologists. And this impactor would have been about the size of Mount Everest when it slammed into the Earth. And what happened is it was moving very, very fast. It would have slammed into the Earth and instantly liquidated a large section of the Earth's crust, or the Earth's mantle, throwing it up into the air and releasing a huge shock wave, also a heat blast, that would have instantly destroyed anything within several hundred miles of this impact. Then the debris is elevated into the atmosphere, circles the globe, rains back down, and elevates the temperature of the planet. So there's massive fires and massive extinction of life everywhere. After that, the dust settles into the upper atmosphere, blocks out the sun, and you have a period of cooling, rapid cooling for several months, even years, essentially an ice age. And it's believed or theorized that this impactor is responsible for the extinction of the dinosaurs. If you look at the geological record, you get to a certain point where there's a layer of what's called iridium. Iridium is an element that's abundant in meteoroids impacting the Earth. And there are no dinosaur fossils after this. So to give you an idea of how much energy was released, the kinetic energy of this impact event was equivalent to 250 million megatons of TNT. So we said earlier that the largest nuclear bomb on Earth was 50 megatons. So this was an extremely energetic event on our planet. And you can see it released energy over 1 billion times more explosive than the atomic bombs that destroyed Hiroshima and Nagasaki. And it was 40 times larger than the Shoemaker Levy 9 impactor that slammed into Jupiter in 1994. So if something like this were to happen today, it would result in the extinction of millions, if not billions of people in a completely altered ecosystem. So that's number 9 on our list.
Can I ask a question about that?
Sure.
So I assume then that at that impact crater that there's a lot of extra iridium.
Yeah, it's present not only at the impact site itself, but it's also present throughout the fossil record.
Yeah, I'm just trying to tie the fossil record to that specifically, and just making sure that evidence is there.
Yeah, I don't think it's necessarily a one-to-one correspondence to the actual impact site itself. I mean, if you look at satellite photos off the Yucatan, you can see a circular pattern. Because it hit just off of the actual peninsula, and a big portion of the crater is actually in the water. As far as the iridium layers, it's actually in areas where you can mine in the mountains and in the canyons. So it's in other parts of the earth. So it's kind of like you put the two and two together. You've got the crater, and then you've got the iridium level when you mine in some of these other areas. And that's supposedly the smoking gun evidence for this event. Does that answer your question?
Yeah.
More or less? Okay. Anybody else have any questions? So that's number 9. Number 8, Martian Impact. So the 112-mile wide crater dwarfs this event early in the solar system's history. And it's believed, well, on the surface of Mars right now, there's a basin called the Borealis Basin. It's the largest crater in the solar system right now. It's 5,300 miles wide, or the size of the continent of Africa. And it's believed that sometime in the early history of the solar system, an object 1,200 miles wide, which is roughly the size of Pluto, slammed into the surface of Mars and caused this event, which is the Borealis Basin. 40% of the surface of Mars is covered by this basin. And it's 200 times, the impactor itself is 200 times larger than the Chicxulub Impactor. And the energy released from this event is equivalent to 1 million times more energetic than the Chicxulub Impact, or the equivalent energy of 200 million megatons of TNT, or of TNT. So if something like this were to happen today, it would obliterate all life on Earth pretty much instantly. And you get an idea as we scale up here, as we go down the countdown, just how energetic some of these events are. The early solar system, it's believed, was a much more violent and much more chaotic place than it is today, because things were still forming. So, again, this is theory. And when you're doing research on things like this, you look for what is, and then you make conclusions or assumptions based on not only the data today, but on extrapolating what could have happened back then. So this is an extremely energetic event in comparison to either the Shoemaker Levy 9 event or the Chicxulub event. So, number 7, what about when entire planets slam into each other? It's believed that this happened sometime in the recent past in our cosmos. And there's a star system called BD plus 20-307. And it's actually in the constellation Aries. It's about 400 light years away. And it has a tremendous amount of dust in the system. It's got 1 million times more dust in it than in our solar system. And it's believed that the cause of this dust is when two planets literally slammed head-on into each other and annihilated each other. So imagine an Earth-sized planet and a Venus-sized planet, and something in their solar system has put their orbits on a head-on collision course with each other, and it basically obliterated each other. So the amount of energy released, of course, is billions of times the world's nuclear arsenal. This would be a rapid extinction of life. You could actually have a little bit of fun imagining a scenario like this unfolding. You know, you're on lunch break, it's a clear day, you walk outside, you look up, and then you see something like this, which is essentially the entire horizon filled from one end to the other with this entire planet coming right at you. And then it's over just like that. These two planets collide, slam into each other, and then just obliterate each other. So it's believed that this scenario actually happened sometime within the last 1,000 years in this star system, in the constellation Aries. So those of you who look at Aries, I don't know what else is in Aries, it's not a very interesting constellation, but again, maybe you look at it a little differently. So these are planetary and asteroid collisions. They release a lot of energy, they do a lot of damage, and if there's any life, obviously, on any of these bodies, those life can be rapidly extinguished or exterminated. But when we're talking about stellar and galactic events, it becomes a whole new ballgame, because stars are so much more massive, and there's so many other processes going on inside of stars, like nuclear fusion, gravitational collapse, other physical properties, other physical forces, and thermal forces that can release a tremendous amount of energy. So before we get into those events, I want to just take a minute here and actually dissect this equation, E equals mc squared, and kind of talk about what it is and what it means and how it works. So it's a very simple equation. It basically is just that energy E is equivalent to the mass of an object multiplied by the speed of light squared. And the speed of light is 3 times 10 to the 8 meters per second. So basically energy and mass are directly proportional to each other. And if you have a small amount of matter, it actually equals a tremendous amount of energy. So we asked the question, let's say you had a dime. And let's say you took that dime and you converted all of the matter in that dime into pure energy. How much energy would you have? How much energy what is the energy equivalence of the mass of a dime? Well, you just plug the numbers into this equation. The mass of the dime is a little over 2 grams. You can calculate the energy pretty quickly by plugging these two numbers in. 3 times 10 to the 8 meters per second. This is the mass in kilograms. So it's equivalent to basically 2.04 times 10 to the 14, and then this is the unit, kilograms, meters squared per second squared. Mass, unit of mass is kilograms, and then the unit of velocity is meters per second. When you square that number, you get meters squared per second squared. So let's talk about units here for a minute, those of you taking a physics class. A Newton meter is essentially this unit right here. A kilogram meter squared per second squared is a unit called a Newton meter, all right? A Newton is a unit of force, equivalent to 1 kilogram meter per second squared. And it literally means the amount of force that you need to push on 1 kilogram of mass to move it 1 meter per second every second, or 1 meter per second squared, which is a unit of acceleration. So the units here are actually a Newton meter. So a Newton meter is the amount, basically the force required to move something 1 meter. It's called a joule. It's a unit of energy or a unit of work or the potential to do work. So that's what a Newton meter is. A Newton meter is a joule, and a joule is a unit of energy. So that's why this equation works, because of the units. Kilograms, meters squared per second squared, which is equivalent to a Newton meter, which is equivalent to a joule, which is equivalent to the unit of energy. So when you plug these numbers in, you come up with 2 times 10 to the 14 kilogram, 2 times 10 to the 14 joules of energy is in a dime. To put that in perspective, break it down, essentially have 204 terajoules or trillion joules of energy, which would be equivalent to the energy released in 3 Hiroshima bombs. Converted into kilowatt hours, you'd have over 56 million kilowatt hours. And in 2010, the average annual kilowatt hour expenditure per household was about 16,000 kilowatt hours. So you do the math here, and it's essentially equivalent to the amount of energy that would power the electricity needs of your house for the next 3,394 years. So if you could take all the mass in a dime, turn it into pure energy, and use that to power the electrical needs of your house, you would have enough electricity to power your house for the next 3,400 years. So, the next time MLG&W comes knocking on your door, because you haven't paid your electric bill, I challenge you, hand them a dime and tell them you don't want to hear them again for the year 5400. See if they understand. So that's what E equals MC squared means, okay? Now, why do we go through this? Because stars are factories that are converting mass into energy. That's what's happening on our sun right now. Our sun converts 600 million tons of hydrogen into 595 million tons of helium every single second. And the difference of that mass is converted into energy, which is given off in the form of light and heat and all kinds of other things. So our sun is literally losing mass over time. But after 5 billion years of burning at that rate, it only loses about 1/10 of 1% of its total mass. That's why it takes so long for a star like ours, a G25 main sequence star, to burn through its nuclear fuel. More massive stars die younger and die harder because they burn through their fuel more quickly. So a star like the Neb in the constellation Cygnus, which is a white supergiant star, is going to blow up a lot sooner because it's a lot more massive. So in stellar events, when you're converting mass into energy, you're talking about a tremendous amount of energy that's being liberated. So that's what we mean by this equation. Now let's have a quick review here of the electromagnetic spectrum. Most of you know what this is. It's essentially all electromagnetic energy from on the long end, which are radio waves and microwaves, to the short end, which are gamma rays and X-rays. And then, of course, in the middle, we have the visible portion of the electromagnetic spectrum. All the, the colors from red all the way up to violet. And visible light actually makes up a very small portion of the total electromagnetic spectrum. And to put this in perspective, let's imagine that the entire electromagnetic spectrum was analogous to a movie reel, okay? And let's say you took that entire movie reel and you just rolled it out. And we're going to assume that that movie reel is 2,500 miles long. So it would extend roughly from here to the city of Seattle, Washington. Maybe a little bit further, all right? So that's the entire electromagnetic spectrum. 2,500 miles wide from here to Seattle. The visible portion of the electromagnetic spectrum would be 1 frame wide, or about 1 inch wide, somewhere in the middle. So that's how small the visible portion is in comparison to the entire electromagnetic spectrum. So when you get here, gamma rays and X-rays, whenever we detect gamma rays, X-rays or gamma rays especially, we know that we're talking about extremely high energetic events. Gamma rays have a very small wavelength, around the order of atomic nuclei, or angstroms. So the amount of energy required to produce gamma rays is tremendous. So that's the signature. That's how we detect black holes. We see the effect that a black hole has on a surrounding star, because it sucks up its matter and then just spews it out. And when it does that, you basically are looking for X-rays and even gamma rays. So that's the signature for an extremely high energetic event. Any questions about that? Okay, so moving along, number 6 on our list are magnetar flares. What on earth is a magnetar? A magnetar is a special class of neutron star that's very rare and very powerful. A neutron star is a stellar corpse that's left over after a massive star blows itself up in the form of a supernova. So when a massive star dies, it fuses all the elements down to the heavy elements. It gets to iron. It can't fuse iron, so it blows up in a supernova. So there's a supernova explosion, but there's also an implosion where the gravity takes over and literally crushes the mass of the body down to a very, very small sphere. And what happens is the gravity is so strong that it literally crushes the structure of the atom from protons, neutrons, and electrons to all neutrons. It's called electron degeneracy, or electron degenerate gas pressure. So the electrons fuse with the protons to form all neutrons. And to give you an idea of how dense this matter is, it's 10 billion times stronger than steel. Another way to think of it is if you had a teaspoon of neutron star material, it would weigh as much as Mount Whitney in the Sierra Nevada. A small pailful of neutron star material would weigh as much as Mount Everest. So if you were to stand on the surface of a neutron star, you'd weigh about 10 billion tons. So you don't want to go there if you're trying to lose weight. So it's extremely dense. It's the densest matter in the universe. So neutron stars fall in two categories. Pulsars, which are more common, like in the Crab Nebula. They rotate very, very rapidly. And then they have a beam of electromagnetic energy that pulses every so often. So that's why they call it a pulsar. It's like a lighthouse. And then you have this category, which are called magnetars. Magnetars were discovered in the late 70s. It's a special type of neutron star with an extremely powerful magnetic field. The magnetic field of a magnetar can be as much as 1,000 trillion times stronger than the magnetic field of the Earth. To give you an idea of how strong that magnetic field is, if one was placed halfway between the Earth and the Moon, about 100,000 miles, the magnetic field would be so strong that it would disrupt all electronic communication on planet Earth, including stripping the information off of every credit card on Earth. So very, very strong. And in 2004, in the constellation Sagittarius, this magnetar, SGR 1806-20, which is located right here. Here's the tea kettle of Sagittarius, right off the tip. That's where that magnetar would be located. You can't see it, too far away and it's too dim. And but this thing blew on this date, and it produced a tremendous amount of energy. To give you an idea of how much energy was released from this magnetar flare, it briefly altered the Earth's ionosphere by expanding it slightly. It blasted the detectors and briefly blinded Earth-orbiting satellites from 50,000 light years away, halfway across the Milky Way galaxy. In 1/10 of a second, this magnetar flare released as much energy as our sun does in 100,000 years. And it was 1,000 times the combined luminosity of every single star in our Milky Way galaxy. So in 1/10 of a second, this magnetar flare in the electromagnetic spectrum released more electromagnetic energy than all of the stars in our Milky Way galaxy combined. It briefly outshined every star in our Milky Way galaxy from an object about 12 miles wide. That's how wide a neutron star is. It's got all that mass packed into that small area. It released energy in the amount of 2,000 trillion joules of energy. All right? If one of these things was to go off at a distance of, let's say the star Sirius, roughly 10 light years away, it would be like, it would destroy our ozone layer, and it would be like every person on Earth being 7.5 kilometers away from essentially a Hiroshima-sized nuclear explosion. It would be like a ton of nuclear bombs going off everywhere. So it would annihilate life on planet Earth. And magnetar flares are very similar to solar flares, where you have a magnetic field, and magnetic field lines get twisted and turned, kind of like a slinky. And then when they do, they suddenly uncoil and release a tremendous amount of energy. So that's the mechanism that causes these flares. It's very similar to solar flares, only they're magnetar flares. Very, very powerful. To date, it's the brightest blast from any object outside of our solar system. If all of the energy from this magnetar flare was in the visible portion of the electromagnetic spectrum, it would have shined brighter than a full moon from 50,000 light years away. That's how energetic this event was. So magnetars, bad stars. You don't want to get too close to a magnetar.
And it only lasted 0.1 seconds.
1/10 of a second. That's how long this flare was. So, and the other thing about magnetars is that it's interesting. You can, The magnetic field is so strong, it can actually deform the crust of the neutron star structure. So it can cause fracturing and deformations, and then when the crust adjusts back, you have what's called a starquake. Similar to an earthquake, they're called starquakes. So, and starquakes would register anywhere from 17 to 18 on the Richter scale, if it was like a regular Richter scale. And when that happens, the magnetic field lines reconfigure themselves and then cause these flares also. So magnetars are fascinating objects to study. I'd love to make my living just studying magnetars. So magnetar flares, number 6. Number 5, how about an entire galaxy blowing out jets? It's called the 100 million year blast. There's a galaxy called MSA 735. It's 2.6 billion light years away. And like all galaxies, most galaxies anyway, it has a supermassive black hole at the center of it that's essentially powering it. And this black hole is billions of times more massive than our sun. And it's sucking up all the energy, all the matter that's swirling around it. So stars and planets get too close to the black hole, they swirl into it, and then they get ripped apart into individual atoms and plasma, and they swirl into this thing. Now, when that process happens, it forms what's called an accretion disk around the black hole. And as the matter swirls closer and closer to the black hole, it starts to speed up. It gets very, very close to the speed of light, and these particles are colliding into each other. And when that happens, they're smashing each other and blowing out all this energy in the form of jets. So this galaxy, MSA 735, has a massive black hole at the center of it that's ripping this matter apart and shooting these jets out. 2 very, very huge jets are being blown out from the center of this galaxy. And these jets are literally blowing, it's like a black hole blowing bubbles. That's essentially what it is. The length of these jets is about 1 million light years long. So 10 times the diameter of our Milky Way galaxy in both directions. And this has been going on for millions of years. Supposedly 100 million years this process has been going on. So now, in terms of total energy output, it's by far the most energetic event that we know of in the universe today. However, because it's been going on for such a long period of time, the energy per unit of time is actually pretty small compared to some of the other things that we're going to be talking about here. You know, we talked about magnetar flares, 1/10 of a second, equivalent to 100,000 years worth of energy expended from the sun. So that amount of energy per unit of time is actually much more impressive than something like this, even though the galaxy itself is spewing out a tremendous amount of energy. But we actually see evidence of entire galaxies being blown away by radiation from neighboring galaxies. In fact, an interesting thing to study would be the Death Star galaxy. It's not this one, but it's something similar where you have one galaxy with a massive black hole that's tearing apart the planets and suns, spewing out a tremendous amount of radiation, and it's actually blasting a nearby galaxy. It's only 20,000 light years away, which is relatively close compared to neighboring galaxies. But you have all this radiation being spewed out from one galaxy to another. So you can imagine that neighboring galaxy, if it had Earth-like planets orbiting suns that could potentially harbor life, they would get blasted by all this radiation from this nearby galaxy that could potentially extinguish life or alter life. So we see evidence of this kind of thing happening. One galaxy literally blowing away another galaxy or ripping apart the matter in its own galaxy. And the reason why it's been happening for so long is because it has a tremendous amount of mass. There's a lot of stars, a lot of matter to rip apart. So it has a lot of fuel. Been going on for 100 million years, probably going on for another 700 million years before it actually runs out of fuel. So, number 5, 100 million year blast. So, number 4, short gamma ray bursts. We talked earlier about gamma rays and how energetic they are. The most energetic events in the universe today are what are called gamma ray bursts. Now, there's different classes of gamma ray bursts. Short gamma ray bursts were recently discovered. And this is actually kind of an exciting discovery because it occurred in a galaxy where there are a lot of mature stars. So not a lot of young stars, but a lot of mature stars that have moved off main sequence and either died or in the process of dying. So what happens in a short gamma ray burst is you have two orbiting neutron stars, two stellar objects that become neutron stars, and what happens is they orbit each other, and they kind of get into what's called a gravitational dance. And this process happens over a long period of time, but slowly their orbits decay, and they start to swirl in toward each other. And eventually they speed up, and then they speed up, and then they literally collide and annihilate each other. And that's the source, or the cause, of these short gamma ray bursts. And what happens is the gravity of one strips apart the other one, so the second neutron star will get flattened into a disk, and the matter will get stripped off of the neutron star and fall on, one neutron star will get stripped off and fall onto the other neutron star. And when that happens, the mass of the second neutron star, of course, accelerates, and there's no force in the universe beyond a certain point that can hold up that amount of matter. So it will collapse into a black hole. And when that happens, these two stars annihilate each other, and they release a gamma ray burst, a short gamma ray burst. So to give you an idea of how much energy was released in this event, back in May of 2005, there was a gamma ray burst called GRB 050509b that occurred in a galaxy 2 billion light years away. And in 0.04 seconds, 40 milliseconds, it released as much energy as our sun will release in 100 million years. That's how energetic these gamma ray bursts are. So, now short gamma ray bursts occur on very short time scales. Typically it's less than 2 seconds. So if it's 2 seconds or less, short gamma ray bursts. 2 seconds or more, long gamma ray bursts. But this is an exciting discovery in astronomy because we now have evidence of orbiting neutron stars in some of these distant galaxies that can produce a tremendous amount of energy when they annihilate each other. So that's number 4, short gamma ray bursts. So number 3, supernovas. We all know what a supernova is. It's when a massive star dies and blows itself up. They exist there's basically 2 main types of supernovas. There's what's called type 1A supernovas, and then there's type 2 supernovas. All right? Type 1A supernovas are when you have white dwarf stars that explode. A white dwarf is a stellar core that's left over when a main sequence star dies. So our sun will eventually collapse into a white dwarf. So more massive stars blow up into supernovas, and eventually they either leave behind a black hole or a neutron star. Less massive stars like our sun will eventually die. They're not going to blow up. It's going to be kind of a boring, uninteresting death. They'll just swell up into a red giant and eventually collapse into a white dwarf. A white dwarf, about the size of Earth, extremely dense. A teaspoon of white dwarf material would weigh about as much as your car does, several tons. Not quite as dense as a neutron star, but still extremely dense. So most stars exist in binary pairs, and the idea is that you have 2 massive stars. One star can eventually swell up into a giant, and then eventually shrink into a white dwarf. And then the other star, when it swells up into a giant, the white dwarf star companion will suck material off of that giant star. It will become massive, and it'll blow up and cause what's called a type 1A supernova. So type 1A supernovas are also good standard, what are called standard candles. A standard candle is a star of known luminosity. It's like a light bulb that's 100 watts. You know how bright the light bulb is. If I tell you it's a 100-watt light bulb, and you know how much power the light bulb is putting out, then you can calculate the distance to that light bulb if you know how powerful it is. So if I tell you it's a 100-watt light bulb, how bright that light bulb is depends on how intrinsically bright it is, but also how close I am to that light bulb. Same thing is true with these supernovas. We know how bright inherently a type 1A supernova is. And because we know how bright it is, we can actually use it as a standard candle to calculate distances to faraway galaxies. So this is one technique that we use, that astronomers use, to calculate distances to really, really far away galaxies, like Andromeda, like galaxies that are billions of light years away. So type 2 supernovas result from the core collapse of a massive star. So you have a star that's maybe 30, 40, even 100 solar masses, and eventually it fuses down to the heavy elements. When it gets to iron, it can't go any further. So it collapses, and then eventually it blows up and causes a type 2 supernova. They release hydrogen. Type 1A, they don't release any hydrogen. What that means is when you're analyzing the light spectra of a supernova, you can tell whether it's type 1A or type 2 based on the emission lines in the spectrum. You see hydrogen, it's type 2. You don't see any hydrogen, it's type 1A. So now type 2 are not, they're poor standard candles. And the reason is because it's very inconsistent in terms of predicting how much mass a star has that produces one of these and how bright it's going to be. So type 1A, yes?
I guess the type 1A and the type 2. Type 2, I'm assuming it's not a white dwarf, it's a larger star?
Yeah.
Okay.
Yeah, type 1A is when you have a binary star system where one companion is a white dwarf and the second one is a star that's moving off of main sequence and swelling up into a giant, and it's putting mass onto the white dwarf, and then the white dwarf blows up.
Okay.
A type 2 is when you have one star, a really, really massive star, that eventually reaches the end of its life, and then it just literally just blows itself to smithereens. So that's a type 2.
Okay.
Type 1A, we know the mass of a white dwarf, and type 1A supernovas are fairly consistent in terms of their intrinsic brightness or their inherent luminosity, so it's consistent. That's why it's a good standard candle for predicting distances. Type 2, the mass can vary. It can be a 30 solar mass star, it can be a 130 solar mass star. So how bright it is depends on how massive it is. That's why it's not a good standard candle for measuring distances.
And I'm assuming, I know that Betelgeuse, I'm assuming it's a white dwarf, and it's supposed to be the closest white dwarf to us. I would assume it would be a type 1A when it turns supernova?
It'll be a type 2. It's
Oh,
not a
it is
white
type 2.
dwarf right now. It's actually a red supergiant star.
Oh, okay,
It's
okay.
moved off main sequence. It's about 15 solar masses.
Okay,
So it'll be a type 2 when it blows up.
okay, I got
Yeah. I actually have a diagram here. This describes the process of a type 1A. So you have basically two normal stars that are orbiting each other in a binary system. Then one of them swells up into a red giant star, similar to Betelgeuse, just not quite as big. When that happens, the gravity of the second star starts stripping material off of the giant star. And so the two become engulfed in this envelope, all right? Then eventually the envelope dissipates, and then the red giant star here turns into a white dwarf. And then the more massive star is still on main sequence. So the main core collapses, comes into dwarf. So now you have a white dwarf and an ordinary star, like our sun. All right? And then what happens is eventually the ordinary star, it dies and it turns into a giant star. And when it swells up into a giant star, some of the material is literally sucked off by the white dwarf. When that happens, thermonuclear fusion ignites in the white dwarf star again. So this star starts to burn again, and when that happens, it becomes unstable and blows up. And that's where you get a type 1A supernova.
Do you know if there's any like distance between the binary stars? I saw something where they were saying that they're considering that our sun itself may be part of a binary star.
Yeah.
That's way out somewhere and eventually is going to come back, and this is going to take place with our sun.
Right. Yeah, Richard
so-
Muller is an astronomer who postulated the theory that our sun might have a dim companion star,
Mhm.
like a red dwarf or even a brown dwarf on the outskirts of the solar system. And our sun is a rare star in that it has no known binary companion right now. The problem is when you study the geological record of Earth, going back several million years, supposedly you can see regular intervals of time where mass extinction events have occurred. And on average, it occurs once every 26 million years or so. So the theory that you're talking about, proposed by Richard Muller, is that on the outskirts of our solar system, somewhere between 1 and 3 light years away, there's a dim red dwarf star that orbits our sun in a very elliptical orbit.
Mhm.
And when it does, its gravity pushes objects in the Oort cloud toward the inner solar system. And then we get the event that we talked about earlier in this presentation, some type of either asteroid or comet collision which wipes out Earth, or wipes out life on Earth. So in a binary star system, though, a distance of 1 light year or more between companions
Mhm.
is pretty rare.
Right.
So in a scenario like this, the distance can vary greatly in a binary system, but typically you're talking somewhere on the orbit, or on the order of, the distance from the sun to Neptune,
Okay,
or from, at most, maybe a quarter to a half of a light year in a binary
okay.
system.
Okay.
Yes.
I can remember years ago when I was in college, binary stars were considered rare.
Oh, is that right?
Yeah, now they're considered norm. There used to be, they thought our sun was the norm, binary stars were the exception.
Yeah.
Now that's flip-flop.
I hate to say this, but you just kind of revealed your age. Because, now we take it for granted.
Yeah.
Binary,
When I was in college, all textbooks said binary stars were the exception.
do you remember when the first discovery was made for a binary star system?
It was in the 50s.
It was in the 50s?
I think so.
It should be Algol and Perseus, if I'm recalling correctly. Yeah, that's the classic.
I don't remember it because I wasn't a teenager at the time.
Right.
I was born in the 50s, so.
You were born in the 50s, yeah. So as our technology, it's another example of how, as technology has improved, our perception of, when I took astronomy back in college, we literally had an entire catalog of different binary star systems we went through. So, fascinating.
And again, each white dwarf has the same mass as each other, as the other white dwarfs.
Yeah.
They're all the
You
same.
you guys understand what a white dwarf is? Who in here does not know what a white dwarf is? Okay, I apologize. All right. A white dwarf is the core or the remnant of a dying star. So our sun is right now is burning hydrogen into helium. Okay? And it's on the it's on a graph of what's called main sequence. So there's a Hertzsprung-Russell diagram which graphs mass and luminosity of a star. So then there's a section of that graph which is called main sequence. So an average ordinary star like our sun will fall right in the middle of main sequence. But eventually what's going to happen is our sun will run out of hydrogen. It'll fuse all of its hydrogen into helium, and then when that happens, gravity will take over and start crushing the star, and then heat will take over, and it'll start what's called helium burning in the core. So the sun will literally swell up into a giant star, okay? And it'll start fusing helium into carbon. And then eventually it'll run out of helium, and it'll start burning carbon. And then eventually it'll run out of carbon, and it'll start fusing heavier elements until you get to what's called iron. Once it gets to iron, it can't go any further. So it'll swell up into a giant star. The outer layers of the star will just kind of float away. And then eventually gravity will take over, and it'll crush the iron core down into an object called a white dwarf. Extremely dense nugget. It's about the size of Earth. Our sun is 875,000 miles wide. So all that mass will eventually be crushed down into the size of our Earth, and it'll have an extremely high density, several tons per square inch. So that's a white dwarf. A white dwarf is basically the nugget or the remnant of a dying star.
And you can still see it. It's still.
Yeah,
It would be hot.
it's still glowing. it's still glowing.
Lights coming from something.
Yeah, the classic example of a white dwarf is the star Sirius. It's not visible this time of year, but in the fall and winter skies, if you look at Orion, you can see the three belt stars. You draw a line down, you can see the brightest star in the sky. That's Sirius. It's called the dog star. And the companion star in Sirius is a white dwarf. You can't see it, but if you had a really, really powerful telescope and you were using a special type of optics, you can infer the difference between the two. So you can, Sirius B is a white dwarf star. So type 1A supernova is when you have binary stars and one of them becomes a white dwarf, sucks matter off of its companion, and then just blows itself to smithereens. That's a type 1A. And so let's talk about, let's just mention one other thing. In order for a star to become a white dwarf, it has to have less mass than what's called the Chandrasekhar limit. It's a physicist named Chandrasekhar back in I believe it was the 30s or the 40s, who got on a boat, traveled from one end of the Atlantic to the other, and all he did was mathematical equations. And he figured out that if a stellar core has 1.4 solar masses, or mass of the sun or less, it'll become a white dwarf. If it has more mass than 1.4 solar masses, the gravity of the star will exceed what's called electron degenerate gas pressure, and eventually it'll crush itself into a neutron star. So now somewhere between 1.4 and 3 solar masses, it'll become a black hole. We're not exactly sure where that is. But if it has 3 solar masses or more, then we know it'll become a black hole. Okay. You guys don't know what I'm talking about, just do what I did in college. Just kind of shake your head. Pretend like, you understand what I'm saying. That's what I used. That's how I got through engineering school. I had no idea what half my professors were saying. You just kind of sit there and just, I understand what you're saying. Yeah, you're crazy. Yeah. So, anyway, back to supernovas. Are there any other questions? Anything I can do to clarify some of this? So, supernovas, observational history. Several have been observed in our Milky Way galaxy over the years. The earliest one actually happened in the year 185. The Chinese observed a supernova in the constellation Centaurus. I'm still trying to figure this out because, to the best of my knowledge, Centaurus is a southern hemisphere constellation, and the Chinese saw it. So how does that work? When you have a southern hemisphere constellation and a supernova, and you get, I don't know. But anyway, that's what the literature said. So this is the first known supernova that was observed. In the year 1006, the brightest, the most intrinsically bright supernova was observed. It had an apparent magnitude of about minus 7.5. So you're on the order of the crescent moon. 1054, the Crab Nebula, the most famous one. And then in 1572, an astronomer named Tycho Brahe observed a supernova. And then later, his predecessor, his protege, Kepler, observed one in 1604. So I want to see a supernova before I die. These guys are spoiled because imagine if you were born in the 1560s, you could have seen 2 in your lifetime. And the last one observed in the Milky Way was in the year 1604. So it's been a while. We're overdue. So these are supernova events that have occurred in our Milky Way. Outside of our Milky Way, 1885 is the first one that was observed in Andromeda. And then, of course, we remember the one in 1987 in the Large Magellanic Cloud, very, very bright supernova. More recently, 2011, last September.
There was one this year.
I'm sorry?
There was one this year.
Was there one this year?
Yeah.
Do you remember where?
Well, I don't remember where, but it was in May, I think.
Was it May?
Mm-hmm.
To read up on that. You don't remember which galaxy it was in?
But here, before you go on, one question about those supernova that's happened in early time, like in his 9th century. The observers who actually saw those things, I mean, how did they describe them? I mean, obviously they had a terminology that we have now. So, I mean, they just said, I saw something bright in the sky.
Okay, classic example, great question. Great question. Classic example, 1572. This is literally what happened. Tycho Brahe, famous astronomer at that time, is taking a walk. He looks up in the sky at the constellation Cassiopeia, and the star in the W of Cassiopeia, he noticed there's another star there, a really, really bright star that just sort of appeared. So he called it a new star or a strange star, and it literally just kind of appeared. It was just there. And it was visible at very, very high magnitudes for several days, and eventually it dimmed out. Same thing is true in 1604. In fact, this supernova event is known as Kepler's star. Going back earlier than that, the Crab Nebula supernova was extremely bright, -6 absolute or apparent magnitude. The more negative the number is, the brighter it is. Okay? To give you an idea of how bright this supernova was, it could be visible 24 hours a day. So you could be walking outside at noon, blue sky, clear day, and see this supernova star. Yes?
And the Chinese are the only ones that recorded it.
The Chinese were the one that recorded it. That's
They're
right.
the only ones, nobody else said anything about it.
Nobody else said anything about it. The Chinese, the ancient Chinese actually kept very, very good records of these stars. In fact, so good that we can go back and predict where they were, position where the actual supernovas were. This one here, this was a -6. This one was a -7.5. So if a supernova goes off in our Milky Way galaxy, and it's sufficiently close to us, you literally will see a bright star in the sky that's visible 24 hours a day for several days. That's why I want to see one of these things. When Betelgeuse blows, it's going to be a spectacular sight. It could blow tomorrow, it could blow 100,000 years from now, but it's getting near the end of its life. So on average, a supernova occurs once every 50 to 100 years in our Milky Way galaxy. One goes off every second somewhere in the universe, but there's hundreds of billions of galaxies. So supernovas are really the thing that we use to measure distances to galaxies and measure distances to the far edge of the universe. It's one of those standard candles. So, but the one in 2011, last September, occurred in the Pinwheel Galaxy, which is located right off the handle of the Big Dipper. It was not bright enough to be seen because it was so far away, 50 million light years. But you could actually see it through a small telescope, and I think even a pair of binoculars. And it was a Type 1A. So how much energy do supernovas give off? Talked about this. In 2003, there was a Type 1A supernova that reached 20 billion times the brightness of our sun for 2 weeks. To date, this is the most energetic, the brightest Type 1A supernova known. And it was so bright that it actually outshined an entire galaxy of stars from an object not much bigger than our moon. So you have a white dwarf that explodes, blows itself to smithereens, and it releases just a tremendous amount of light and a tremendous amount of energy. So this event right here could easily exceed the total energy output of our sun over its entire 10 billion year lifetime. The other thing that makes this event so interesting is that it was what's called an aberrant Type 1A supernova. What that means is it's one of the rare supernovas where the core actually reached more than 1.4 solar masses before it blew up. And it's believed it's because it was rotating so fast that it was able to take on more mass before it eventually exploded. So it's sort of rethinking in the astronomical community the reliability of Type 1A supernovas as a standard candle for measuring distances. If some of these things can actually get more massive than the Chandrasekhar limit. Now, Type 2 supernovas, there was one in 2005 that occurred in a galaxy 4.7 billion light years away. Extremely massive star, somewhere on the order of 130 to 250 solar masses that blew itself apart. And to give you an idea of how bright this supernova was, it was 20 to 200 times brighter than the supernova in 1987 that occurred in the Large Magellanic Cloud, or 100 billion times brighter than our sun. Tremendous amount of energy that was released in this supernova explosion. So these are two of the most massive, most energetic supernovas ever recorded, and they occurred in the last decade. And we're seeing more of these types. Yes?
When you say energy, you're talking about the entire spectrum, not just
Yeah.
or visual or anything else. You're talking about total energy throughout the spectrum.
Yes, I am. And really, when I'm talking about energy, I'm talking about the kinetic energy of the ejected material.
Okay.
So when a star, you know, when a supernova, a type 2 supernova explodes, what happens is you have the stellar core which contracts. And then when it contracts, it rebounds. And when it rebounds, it meets the mass of the lighter outer layers of the star which are falling in, and they receive a kick. And it literally blows that material out. So when that happens, the kinetic energy of the ejected material, the kinetic energy or the energy of motion of the ejected material can easily equal or exceed the energy output of our sun over its entire 10 billion year lifetime. That's how energetic these supernovas are. So that's what I'm talking about here. And the energy that's released, or the energy of the material, the velocity of the ejected material can reach 10% of the speed of light. So this is basically the process by which heavier elements are seeded into the universe. You know, you have these stars that start out burning hydrogen and helium lighter elements, and then when they die and they explode, they blow these metals out, you know, oxygen, calcium, iron, all the elements of the periodic table, the heavier elements, ultimately is believed to come from type 2 supernova explosions. So that's supernovas. So, number 2 on our countdown is long gamma ray bursts. We talked about short gamma ray bursts earlier, which occur when orbiting neutron stars collide into each other and annihilate each other. Long gamma ray bursts are gamma ray bursts that occur over periods of time of 2 seconds or longer, and they come from massive stars dying. So what happens is, it's like taking, you know, when supernovas and magnetar flares release their energy, they release it in a spherical motion. Now imagine taking all that energy and concentrating it into a jet, like a shotgun, and blasting it all out. That's what happens in a long gamma ray burst. So you have concentrated jets of energy that shoot out of the poles of a dying star, and the energy, the material is moving at a significant fraction of the speed of light, 99.999% of the speed of light. And it comes from the explosion of supermassive stars, 30 solar masses or greater, that blow themselves apart. And what happens is, similar to a supernova explosion, the iron core collapses, rebounds, and material continues to fall onto the iron core as it's collapsing. When that happens, it can no longer hold up because it's got too much mass. Gravity takes over and literally crushes itself out of existence. The temperature rises to 10 billion degrees Kelvin. The luminosity of that dying body per cubic inch is equivalent to the total luminosity of our sun. So imagine taking all the light energy. Yes?
You know what I guess the exit of all the mass that is shooting out, you know if it exits it through the axis of the rotation, or if it...
Yes.
Okay.
Yes. It's not clear here. Yes, that's exactly what happens. You have a rapidly rotating body. It blows up. When that happens, it shoots out these jets, these gamma ray jets, along the axis of rotation. So
Does it actually, I mean, is the core collapsing on itself, or is the entire star collapsing on itself? Or
It's
no?
the entire star.
Okay.
which at this point in time is the core, because the outer layers have been blown off.
Oh,
So
okay.
it's a massive core that cannot, it's a core, it's a stellar core whose mass is so great that it can no longer exist. So it's literally blowing itself apart and crushing itself into a black hole. So more matter is falling onto it, so it can't become a neutron star because it has too much mass. So it's turning into a black hole. In the process of turning into a black hole, it annihilates itself, it collapses, and it shoots out these gamma ray bursts. So that's the mechanism that causes this. So the power can't blow out of the equator, so it blows out the poles. So you have all this energy being blown out of the poles of these stars. So, and it's the evidence of a black, this is the evidence of the birth of a black hole. Supermassive stars dying like this, with a massive rotation. So let's talk about how much energy a long gamma ray burst can actually spew out. It's 10,000 times more powerful than a short gamma ray burst. A short gamma ray burst in 40 milliseconds spewed off more energy, released more energy than our sun does in 100 million years. This thing is 10,000 times more powerful, these long gamma ray bursts. Now, two of the most famous long gamma ray bursts. The first one is called GRB 080319b. And it occurred on March 19, 2008. And it was in the constellation Bootes. For those of you who don't know where Bootes is, you basically have the Big Dipper. And if you draw a line from the handle of the Big Dipper, you'll run into a very bright star called Arcturus. It's one of the brightest stars in the sky this time of year. That star is in the constellation Bootes. So this gamma ray burst occurred in that constellation. It was 7.5 billion light years away. All right? The peak apparent magnitude of this gamma ray burst reached 5.8 for 30 seconds. Now, the naked eye on a dark night can see objects out to +6 in the sky. You can distinguish them, you can see them. So this gamma ray burst was so powerful that it was literally visible to the naked eye for 30 seconds if you happen to be looking in the sky at the time that the light from this event reached us. So you're talking about being able to see an object 7.5 billion light years away, halfway across the universe, with the naked eye, if you happen to be looking at the sky at that point in time. That's how bright this gamma ray burst was. What's the most what's the most distant object that can be seen with the naked eye? You guys know? It's Andromeda Galaxy. It's, well, some say it's Andromeda, some say it's Triangulum. Typically it's the Andromeda Galaxy. It's about 2.5 million light years away. That's the most distant object in our universe that can be seen without a telescope. This thing, when it blew up, it was visible to the naked eye from 7 billion light years away. That's how bright it was. So that's incredible. The peak energy flux was 10 to the 44 watts in visible light alone, and it was 2.5 million times brighter than the brightest supernova to date, which is the one in 2005. So this gamma ray burst is an example of just how powerful these things are and how bright they are. If one of these things was to go off in our galaxy, even at a distance of several thousand light years away, if these gamma ray jets were pointed in the direction of Earth, it could easily annihilate all life on Earth. That's why we're keeping our eye on some of these stars, like WR104 in the constellation Sagittarius. It's a Wolf-Rayet star. It's 8,000 light years away. But when it blows up, it's going to be a supernova. And if it does blow up and become a supernova, it could produce a gamma ray burst. Not likely, but it could. And it's just right on the edge of the danger zone. 8,000 to 9,000 light years away. Where if we're in the path of that gamma ray burst, they could do significant damage to our ozone layer and to life on Earth. So these things are very, very powerful. It was the most intrinsically bright object ever observed by humans in the universe. Second gamma ray burst occurred on September 16, 2008. And this is actually the most powerful gamma ray burst ever recorded. It was in the constellation Carina, 12 billion light years away, so near the edge of the observable universe. And it lasted for an incredible 23 minutes. Most gamma ray bursts only last for a few seconds, even the long gamma ray bursts. This one lasted for 23 minutes, and it had a power of 9,000 supernovae. The total isotropic energy was equal to a very big number, which is equivalent to taking all of the mass of our sun, roughly 5 times over, and converting it into pure energy. That's how much energy was released in this gamma ray burst. So we talked earlier about how much energy is equivalent, what the energy equivalency of a dime was. 3 Hiroshima bombs. Our sun is extremely massive. Over 99% of all the mass in our solar system is the sun. Imagine taking 5 of our suns and converting it into pure energy and then concentrating that energy in a beam. And that's what you would have from this gamma ray burst. It was by far the most powerful gamma ray burst ever recorded, and the energy released was greater than our sun's total energy output over its entire lifetime. Very, very powerful. So the bottom line is that gamma ray bursts can easily exceed the total light output of millions of galaxies. And this is where my mind starts to get stretched to the breaking point. How can you have a star, an object? I know stars are big and they have a lot of mass, but how can you have one star, when it blows up, that releases so much energy that it actually outshines not one galaxy, but millions of galaxies? That's what you get in a gamma ray burst. Gamma ray bursts are very, very powerful, very, very energetic events. So, but there's one other thing we need to talk about. That's actually number 1 on our list. And that's called rapid inflation. And this is, in the countdown, the most energetic event in the history of the cosmos. Now, what is rapid inflation? Conventional theory says that the universe had a beginning in an event called the Big Bang that happened about 13 billion years ago, and it's also called, I find it interesting, the terminology for the Big Bang. It's called the moment of creation. Our perception of the universe has changed a lot over the last century. For years, scientists, including Einstein himself, adopted a model of the universe known as the static eternal universe. And I think it was more for aesthetic reasons. Scientists back in the early 1900s didn't want to think about a universe that had a beginning. But when Hubble came along and started observing distant galaxies and the redshifts in distant galaxies, he really proved the theory that was proposed by a man named George Lemaitre earlier in the 20s, that the universe had a beginning. The universe is finite, it began, and there was a moment of creation, and it's expanding. Now, the Big Bang term is kind of a misnomer if you think about it. If all the mass and energy in the universe at one time was compressed into a very, very small sphere, then it wasn't big, and there really was no bang. So, and the Big Bang really doesn't talk about the actual event that caused the origin of the universe. It's really talking about the events that happened immediately after whatever brought the universe into existence. And the conventional Big Bang theory model doesn't really work unless you integrate this component to it, which is called rapid inflation. And rapid inflation really says, what rapid inflation is really about is it's describing the bang in the Big Bang, which is a time in the universe when there was rapid inflation, where the universe literally doubled in size and expanded exponentially over an extremely small period of time. So it started out as nothing, and then it instantly doubled and tripled in size many times over. And this happened over a very, very small interval of time. A millionth of 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 a second. It was originally proposed by a man named Alan Guth in 1981. And his his ideas for the rapid inflation theory were an expansion of in what's called a false vacuum. A false vacuum is when you have a lot of mass and energy compressed into a very, very small sphere. You have high density, high energy, and gravity actually acts as a repulsive force rather than as an attractive force. So it blows things apart. So this region would have doubled in size every 10 to the minus 37 seconds. And it doubles again, and doubles again, and doubles again. And the idea is this false vacuum decays over a period of time and then gives way to the more gradual or normal, quote unquote, normal expansion, which is predicted by the Big Bang theory. So this model has been under analysis and revision many times over, including Lindy, Albrecht, and Steinhardt, who solved a lot of the problems of Guth's model and came up with other inflation models called new inflation, chaotic inflation, eternal inflation. The bottom line is, in order to make the Big Bang work, you can't think of a single point where everything blows out like you would in a normal explosion. You need to have an inflationary period, a period of rapid inflation, because it solves a lot of the problems that the Big Bang, the original Big Bang theory, had the more you analyze it, and that is why the universe appears to be flat, homogeneous, and isotropic, which it wouldn't if you had a normal Big Bang without rapid inflation. And then also the lack of abundance of heavier elements called monopoles. These are massive subatomic particles. The bottom line is, without inflation, the density, the matter density in the universe should be a lot higher, 15 orders of magnitude higher than it currently is today. So the Big Bang theory is still kind of, it's a work in progress. It's a theory. More and more it's becoming accepted. It is the more widely accepted version of the origin of the universe, especially because of the discovery of the cosmic microwave background in the last decade. But it's still very much a model that needs tweaking and revision. It's a work in progress. And it's not simple. I mean, there are parts of the universe that are chaotic in terms of its expansion, and then there are parts that are stationary. So there's a lot of moving parts to it. As far as rapid inflation itself, it has not been proven concretely yet that it did in fact happen. One of the theories, or one of the hypotheses of predicting rapid inflation is by detecting what's called gravitational radiation ripples in the fabric of space and time. So the idea is space-time is like a rubber sheet. You have mass, which distorts space and time, Einstein's general theory of relativity. If this mass or energy is moved, a lot of mass and energy is moved rapidly, then it'll cause ripples in the fabric of space and time, and you should be able to detect these ripples. And there's actually work being done right now at the Laser Gravitational Wave Observatory in Louisiana to try and detect this gravitational radiation. And it's thought that once this gravitational radiation is detected, that will be the smoking gun evidence to prove that this period of rapid inflation did in fact happen early in the history of the universe. However, Lawrence Krauss and his team has published a paper lately stating that gravitational radiation can actually be caused by something called symmetry breaking instead of just rapid inflation. So the bottom line is, even if we were able to detect gravitational radiation, that doesn't necessarily prove that this period of rapid inflation did in fact happen, because there could be other causes of it. So, bottom line, we know in the last century, we've gone from the perception of the universe being static and eternal to being finite, having a beginning, and dynamic. In other words, changing. The universe is expanding with time, and the rate of expansion is accelerating with time. It's another reason why I think the Big Bang theory or the Big Bang model is not really accurate to describe what we're seeing in the universe today. The universe is expanding with time, and the rate of expansion is accelerating with time. And that's because there's something going on that we don't completely understand yet. It's called dark energy. Dark energy is literally driving the galaxies apart. It's a mysterious force that we don't completely understand yet. We know it exists because we see its effect, just like we know that dark matter exists because we see its effect. But we have no tangible proof yet for its existence. So, rapid inflation and dark energy, is there a correlation? Is there a relationship? Maybe, we don't know. But the universe is expanding, not from a central point like you would get from an explosion. And then also with an explosion, you would think that over time, that explosion would dissipate, slow down, and eventually gravity would take over and start crushing it. That's not what we're seeing. The universe is essentially flat, linear, homogeneous, and expanding. The more distant regions are expanding more rapidly than the regions closer to us. So, dark energy, dark matter, the greatest mystery in the universe today. And it's something I'll be focusing on if I ever get a chance to speak to you guys again. But this concludes my presentation on the 10 biggest blasts in the history of the cosmos. And does anybody have any questions?
What do you think of mass? Do you think it doesn't increase or it doesn't decrease, it just changes shape?
I'm not one that personally subscribes to a theory of the universe where mass is being constantly created or injected into the universe, like Hoyle's steady state theory. So I would tend to believe that mass is either converted into energy. Basically, I subscribe to the law of conservation of mass and the law of conservation of energy. It basically states that mass is either remaining static or it's being converted into a form of energy. Does that answer your question?
Well, what happened to energy? Where does it go?
Where does it go? Energy dissipates. It either dissipates.
It's got to be in the universe, though.
Absolutely. What do you mean?
That's what I'm saying. It's just rearranged.
You can't disappear, you just.
No, it can't disappear. It has to be conserved.
Spreads out more.
It's just rearranged.
Well, it converts from one form to the other. It can be light energy. It can be energy of, it can be potential energy, gravitational potential energy, heat, obviously. It just basically is transferred from one form to another. So, is that what you mean by your question?
That suits me, yeah.
Okay.
Well, some theory is that, all the water that's on Earth today has been here all along. It's just different places, different times, in the atmosphere or in the ground or wherever.
Right. Is more water being added to or subtracted from the Earth?
Whatever anybody want to believe about something like that, it's okay with me. I don't give a hoot. Yeah, and nay.
And back to the dime and converting all that into energy. So the big nuclear bombs that got dropped on Nagasaki.
Right.
Just a third of a dime was all. See how big the bomb is. About a third of the time is all that actually got used.
No, not quite. We're assuming 100% efficiency, or that 100% of the mass is converted into energy when I was doing this analysis of the dime. In real life, that doesn't happen.
Okay.
So, like the atomic bombs, take Little Boy, for example, which was a uranium bomb. What you had was basically two fission fragments that were slammed together to form a critical mass. All of the matter was not converted into pure energy. It was one form of matter that was converted into a smaller amount of matter, and then the energy, the difference, was released. So, there isn't a. When the atomic bombs were built, it's a conversion of a certain amount of mass into a smaller amount of mass. But you're not converting 100% of the mass into energy with 100% efficiency. Does that answer your question?
Yes.
All right.
Well, take water, for instance. It's in a vapor form in the clouds, in the atmosphere. And it floats around. It turns into a liquid. A gallon of water weighs around 9 pounds, right here.
Mm-hmm.
Just think about how much vapor up there can turn into, weight.
Oh, absolutely. I mean,
It's unbelievable that it can happen, but it does happen.
you have water on the surface of the earth in the form of lakes, streams, oceans, water under the earth, and then you have water vapor up in the atmosphere. Lots of water vapor. So yeah, I mean, and then that water can rain back down onto the earth, and when it does, eventually the sun the thermal energy from the sun will heat the earth's crust, and then that water will evaporate again, and then it'll turn into water vapor. So,
That's what the sun's doing, is drawing water back up, evaporating it, so to speak.
yeah, it's all part of the hydrological cycle. Trying to remember.
Question about the gravitational radiation, how fast does that travel?
That's a good question. It's a significant fraction of the speed of light. I don't know the exact speed that gravitational radiation. The reason why that's such an interesting question is because you're talking about the fabric of space and time itself, in other words, space itself. Einstein's special theory of relativity says you can't go faster than light in space. But the general theory doesn't restrict space itself from expanding faster than light. So you could make the argument that gravitational radiation could actually ripple through the fabric of space and time faster than the speed of light. And that's the theory behind inflation, that space itself expanded faster than light early in the history of the universe, which is why you essentially went from nothing to everything in an instant. And you had this uniform, homogeneous universe. So the short answer is I don't know, but you could think of gravitational radiation as actually propagating at or even faster than light if you think that space itself could actually expand faster than the speed of light.
Well, but when space was going faster than the speed of light, one could question what the measurement of time was at that very dense manner.
Right.
So the fact that the universe could expand faster than the speed of light at that point in time is different than today. 12 billion years after that, with the gravitational waves going faster. I don't know.
Yeah.
Just a question.
I don't know either. It'd be interesting to research that further, especially when you think about dark energy's influence on the outer reaches of the universe. It's expanding, and it's not only expanding, but the rate of expansion is accelerating. So it's expanding faster with time. So, all right, guys.
Tim?
You're an Iron Man. I can't go before 12 minutes.
Yeah.
Tim wants to attention for a minute or two here.
Yeah, thank you, Jeremy. That was very fascinating. I don't have a presentation, so don't worry. I just wanted to make everybody aware, maybe you've heard of it in the news, or you might be hearing of it in the news in the next couple of days. But
It's on the news tonight.
was it? Okay. There's a NASA mission that is going to land a 1-ton rover on Mars this coming. It'll be like Sunday night, about 12, just after midnight, 12:30. So it'll be early Monday morning, technically. But it's called the Mars Science Laboratory. The rover's called the Curiosity. It's 1 ton. I mean, it's huge in comparison to what's been up there before, and the entire way that it's getting to the surface is just totally fascinating. And I would encourage people to if you have internet access, go to www.nasa.gov/MSL. That stands for the Mars Science Laboratory. And there's a lot of information about the rover, what scientific experiments it's going to have. But more than anything that fascinates me is the procedure that's going to happen during the landing process. And there's a video linked on that site called, I think it's 7 Minutes of Terror. And like in the last 3 minutes of its descent, there's a supersonic parachute bigger than anything that's ever been done before to slow it down. Then there's rockets to slow it down further, but the rockets don't take it all the way to the ground or the surface of Mars. In the final few minutes or seconds, it's lowered on a tether. They're calling it like a sky crane, rocket-powered sky crane. Sounds like something out of a science fiction novel. And I've watched the video a couple times. It's really fascinating. And so you might be hearing about this Mars Science Laboratory and the Curiosity rover this weekend. I'm just totally fascinated by it. I just wanted to share that in case you want to go out to the internet, read about it some more, see that 7 minutes of terror video. And just if it works, it's just going to be a miracle. But that's what NASA does, you know, and a lot of times is come up with miraculous things. And I hope that some future time, if everything's successful, or maybe even if it's not, I'll do a presentation on exactly what happened or what it's going to do. But it's going to have a 2-year life once it lands. Doing scientific investigations. So just wanted to make you aware that that's happening this weekend, and hopefully you'll go and read more about it.
They can't bounce it down like they did the road.
It's too big, you know.
So it won't have the
Weighs like
airbags?
No, the previous one landed like with airbags. They were just insulated with the kind of circular spherical airbags, and just bounced along until it stopped. And
this one weighs a ton.
yeah, it weighs a ton. So I mean, once it gets low enough, it's going to be lowered. The rocket part's going to be here, and it's lowering it on a tether, on a like a crane or something, to the surface. Once it's on the surface, there's pyrotechnics to break away the tether, and then this part, the rocket part, flies away and crashes somewhere, and then the rover is there, hopefully. And it's like, the more I read about it, it's like, it's just totally fascinating. So I just encourage people to go read and investigate a little bit more. And you'll probably hear about it in even more.
They showed it on NBC.
It's gonna be on NBC Sunday night,
And
and it was mentioned in the news this evening.
okay, I didn't see the news this evening, so everybody probably already knows about it, but I just wanted to make everybody aware. Late Sunday night, early Monday morning, it's supposed to land. The really cool thing too is that it was launched just this past November. Let's see. Yeah, it was in November of last year it was launched, so it's a fairly quick journey to Mars, and but it's so far away that it takes the radio waves 14 minutes to reach Earth, the way everything's positioned right about now. So the 7 seconds or 7 minutes that it takes to go through its from orbit or it doesn't even really go in orbit first, but as it descends to the surface, NASA won't even know if it was successful or not, for 14 minutes after that point in time. So it's a really cool thing, and NASA doesn't have the space shuttle anymore. So I look to these things for my grins and giggles, and it's just a really cool thing. So I encourage you to find out more about it.
Is it like a vehicle that moves around, or is it a station?
No, it's a rover, a 1 ton. I think it's got like 6 wheels, and I think it's an all,
very similar to
6-wheel
the
drive thing. It's got 10 scientific instruments on it, 7-foot long boom arm, and it will.
It's just a Greyhound rover.
It doesn't use solar panels. It has a fusion generator that generates electricity. And one of the instruments is a laser that will be able to melt rock. Okay, to vaporize rock, to analyze the minerals on the vapors.
So does this have anything to do with the Mars colonization project?
No.
Or no?
No.
But it is looking for signs of past life.
Mm-hmm.
It's got more advanced technology experiments than previous expeditions, and the generator you were talking about, if I remember correctly, it generates 110 watts of power. And that, I mean, that, you know, that light bulb is 100 watts typically. And so it's going to be running for the next 2 years on 110 watts that's being produced by the reactor type thing that's on there. So, like I said,
It's the last one.
what's that?
That is the last reactor Banza has. They don't have any more.
Okay.
Because the government imposed a ban of those kind of generators being launched to space.
Because they're afraid that it.
Oh, yeah, they're afraid it will explode and contaminate the whole world.
Yeah. So that's interesting. I'll see if I can put together a presentation on this for the future, but just wanted to let everybody know that this is happening this weekend. And that's all that I have. Thanks, Chair.
Yeah.
As always, thank you.
That'll do us for this time. Hopefully, the observing session's coming up. We'll meet here the first Friday of next month.
It's fine.
Hey, thanks for coming out.
So you're there, I got about 45 minutes to get out, jump forward.
I'm sorry, you got it.
You like warm up?
Yeah.
No, just for.
Did they say,
Yeah.
yeah, how far away is that?
Jeremy's
What's that?
You must be there. I don't know.
Thanks. What's that? Want to do a second? Thank you. I haven't got a chance. Okay, I will. Okay.
Take care, man. I'm taking out a couple of lines.
But you had it.
Yeah.